In the previous lecture, we talked about airfoils, airfoil nomenclature. We said that an airfoil could be thought of as a chord line, which is simply a straight line that goes from the nose of the airfoil to the trailing edge. Then to the chord line, you add a camber. Camber makes it asymmetric. If you don't have any camber, it's a symmetric airfoil. Then you add a thickness normal to the camber line by convention to add the thickness. So an airfoil is made of three components: chord, camber, and thickness. We said the angle of attack is the angle between the free stream velocity and the chord line. We also talked about the angle of zero lift. At certain alpha, usually a negative angle of attack, the CL becomes zero for cambered airfoils. So in our lecture, we called it alpha naught. So all these things are shown in this particular picture. Today, we are going to talk about how NASA started naming their airfoils and then what is the convention that they followed. I have a web link to this particular website in our Canvas site, so you'll be able to revisit this site anytime and read up more on this. During the 1930s and also early 1940s, when the aviation industry was just evolving, current NASA that we know used to be called NACA, National Advisory Committee for Aeronautics. So they used to have a wind tunnel at Langley, what we currently call NASA Langley Research Center. At the time, it was the Langley Lab. They had a lot of wind tunnels where they would test airfoils, and then they would also make data available. How does the lift, drag, and pitching moment vary with angle of attack? So this was done by NACA, and they had to have a way of naming the airfoils and evolving it as advanced airfoils became available. So the simplest airfoil is called a 4-digit airfoil. So we are going to first look at it here. A 4-digit airfoil basically will have 4 numbers, numerical numbers. For example, in the X-foil project that you'll be doing, you're looking at a NACA 0012, which is a 4-digit airfoil. You're comparing it with the NACA 2412, which is also a 4-digit airfoil. So what do these different numbers mean? What does 0012 mean? What does 2412 mean? So this is the explanation. The very first digit means how much is the camber, maximum amount of camber as a percentage of the chord. For example, if you have a NACA 2412 airfoil, the number 2 means 2% camber is the maximum amount of asymmetry that you have as a percentage of the chord. So if the chord was 1 meter, this would be 2% of 1 meter, which is like a 2 centimeter. The second digit, which is this 4, means the distance where the maximum camber occurs measured from the leading edge in tenth of the chord. That means 4 means 40%, 4/10 of the chord. That's where the maximum amount of asymmetry occurs. The last 2 digits are the percentage thickness of the airfoil, maximum thickness of the airfoil between the upper surface and lower surface as a fraction of the chord. So 12 means 12% thick, maximum thickness. Obviously, we want a very thick airfoil, if possible, because then structurally you could put all the structural elements inside the airfoil to make it very strong in bending and torsion. You could also have a large storage area for fuel tanks. You will also have some real estate for putting actuators and so forth for actuating flaps and ailerons. So we'll try to get a very large, thick airfoil. But a thick airfoil also means very heavy wing. Also, if you make it overly thick, the flow may get separated in the back end of the airfoil, causing stall or perhaps at least a rise in drag. So many factors go into play. For this reason, most of the airfoils tend to have about 12% thickness. So occasionally you will find a 15% airfoil, thick airfoil. For example, McDonnell Douglas had a huge helicopter long time ago. It had a 15% NACA 0015 airfoil as a airfoil that they used. Here is NACA 0015 airfoil. 0 means zero camber. So we don't need to say where the maximum thickness occurs. It's at 0%. All over the airfoil, there's no camber. It's 15% thick. So this is what 4-digit airfoils are called. NACA also has got a 5-digit, 6-digit, 7, and so forth. At some point, they stopped defining their own airfoils because the industries such as Boeing, McDonnell Douglas, Grumman, other companies started developing their own proprietary airfoils. Therefore, they no longer needed a NASA's help in defining airfoil. They also had their own wind tunnel where they would test the data, and they wanted to keep it to themselves, so it became a proprietary information. So let's go to how is the geometry of a 4-digit airfoil defined. There are some analytical curves that are available. For example, for a thick airfoil, once you know the thickness, which is the percentage, then you can define the Y value of the thickness of the airfoil using a curve such as this. X is the position of the chord from 0 to 1. So, for example, 10% means 0.1, 20% means 0.2, and so forth. Middle of the chord would be 0.5. And T is the thickness. It's also a fraction of the chord. For example, if it's a 12% thickness, T would be 0.12. So, for example, when x equal to 1, all of these things will go to 0. And when x equal to 0, all of these things will go to 0. So you'll start with 0, end up with 0. Then this will show you how the curve is changing upper and lower. You don't need to use this equation in any of our projects or homework because Xfoil already has all this information embedded in it. So we would not have to construct the actual airfoil, but it's interesting to know how the airfoil is constructed. Now, for a cambered airfoil, you need to, on top of it, you need to add a camber. So depending on the amount of camber and also where the maximum camber occurs, you would use a curve upstream of the maximum camber and then the downstream of the maximum camber. There'll be two locations where you'll use two different equations. So again, when you go to maximum camber, you'll go to 0 when x equal to 0. You'll go to 0 when x equal to 1. So when x equal to 1, this and this will become 1. This 2p will cancel with this 2p. So, that's how the various equations work. Okay. So again, you don't need to construct any of these things. Let's go to the 5-digit airfoil. It's a more complicated. It's got 5 digits to it. 2, 3, 1, 1, 2, for example, is an example. Again, the last 2 digits are the same. 12 means 12% thickness. TT. LPSTT is how we should remember. TT is the thickness to chord ratio. 12% thickness as a fraction of the chord. So if the chord is 1 meter, the maximum thickness, the total thickness between the upper surface and lower surface is going to be 12%. How about the other digits? The L, which is the first digit, means the best lift coefficient for which you have designed this particular airfoil. That means in this particular airfoil, the optimum lift coefficient is 0.15 times 2. You have to make it 15% of L. So this is 2. So 0.15 times 2 is 0.3. Therefore, this particular airfoil was designed to perform the best. That means the lowest drag at a lift coefficient of 0.3. We want to keep the lift high. We want to keep the drag low. So this is the optimum lift coefficient. How about the second digit, which is the P, is the x-coordinate of the maximum camber. For example, it is 0.05 times the letter P. So if you have a 3 times 0.05 is 0.15, which is 15% of the chord. That's where the maximum camber occurs. S is a single digit, asking whether the airfoil is a camber is a very simple curve like a parabola. Does it have a reflex? That means does it have a convex part as well as a concave part? That's all this one is. This number 1 is. Okay. Then finally the 12 means 12% thick. This is a 5-digit series airfoil. Likewise, they have developed a 6-digit, 7 digits, and NACA stopped developing their own airfoils at some point, and industry started developing their own airfoils. So here are airfoils that we talk about. Later on, we'll talk about supercritical airfoils, primarily for transonic flow. When we get to compressible flow, chapter 11 in our textbook, we will go to supercritical airfoil. So this is a very short exposure on airfoil families and airfoil series. In our Xfoil project, we are going to primarily be looking at 4-digit series airfoils, but you could also do similar analysis of any of these family of airfoils. So that should be one of your project that you'll be working on. That project is worth 10% credit. Therefore, the next video will cover how to work on the Xfoil project.